Welcome back to the next video, everybody. This is 13.7, defining the flat deformation functor. I'm sorry to have been away for a while. I've had some significant personal and professional issues arise recently that I'm trying to work through. But I'm back on the horse, so let's get into it. If you recall from the last video, to finish the proof of r equals t, we just have to formally define the flat deformation functor and prove Ramakrishna's theorem on its representability. So for the rest of the chapter, what we'll do is we'll fix some notation. O will be the valuation ring of a finite extension of QP. Lambda will be a uniformizer, and K will be O mod lambda, the residue field, and that'll be of characteristic P. We'll choose a continuous flat representation rho bar from GP to GLN of K. And just keep in mind, we'll eventually specify to the case where n equals 2, P is odd, and rho bar has cyclotomic determinant when restricted to inertia at P. Okay, now it seems like we don't really need to work in this level of generality, and it is true that we are ultimately interested in the case where rho bar is rho bar EP restricted to GP, which is the GP representation arising from the P torsion of an elliptic curve E over Q. However, it's also the case that we're going to have to extend the field of scalars from FP up to a finite extension K that contains all the eigenvalues of the finite subgroup rho bar EP of GQ inside of GL2 of FP. We saw this actually in the proof of R equals T in the general case. And so we actually do need to work in the generality that we claimed on the last slide, even though our ultimate goal is specification. Okay, so setup, we'll let du rho bar denote the universal deformation functor attached to rho bar on the category C hat O of complete local Noetherian O algebras that have residue field K. If rho bar is absolutely irreducible, which, for example, happens if rho bar is rho bar EP for some elliptic curve E over QP with supersingular reduction, then du rho bar is representable by the main results from chapter 8, section 20. So chapter 8 was the section on Mazur's deformation theory. Okay, we've got this universal deformation. We have representability. That means we have a universal deformation ring. Let's call that RU rho bar. Unfortunately, we can't actually just outright assume the absolute irreducibility needed to get the representability we're talking about, because in certain special types of ordinary cases in Weil's proof, we will need more general results to do so. Okay, so like in the supersingular result, we're all set, but in certain ordinary cases, we're not. Let's recall that there was a key step in Weil's proof that computes the orders of GP cohomology groups attached to certain deformations of rho bar. Okay, so we've already sort of been through these calculations, but let's recall from that discussion that from the deformation functor point of view, these computations amount to computing other things, namely the size of certain distinguished subsets of du rho bar of A for suitable Artinian objects A in C hat O. So for example, when A equals O mod lambda to the n, that's kind of a big thing that you have to be able to understand. If a representing ring RU rho bar exists, so again, as I said before, this happens if rho bar is absolutely irreducible, for example, then we know from results that we've been dealing with since as far back as chapter 4 that du rho bar of A is just C hat O homomorphisms from RU rho bar to A. And so if we could really just determine the structure of RU rho bar, we would be in really good shape to do these computations. Okay. In order to do this, we will actually have to finally define the flat deformation functor, which I'm going to do now. Okay. So for A in my category C hat O, meaning for an object A in that category, define d flat rho bar of A to be the subset inside du rho bar of A, so the full deformation problem, consisting of those deformations of rho bar to GLN of A whose representative liftings, rho from GP to GLN of A, have the property that for all n bigger than or equal to 1, the finite GP module rho mod m sub A to the n is flat, where m sub A is the unique maximal ideal of A. Okay, so that we're basically looking at flat deformations. Okay, now, does this make sense? Well, we do know that flatness is a property of isomorphism classes of finite discrete GP modules. We've known that since as far back as, I believe, chapter 4, so this is well defined. Also, by Theorem 14.3.3, which is Renault's equivalence of categories, you can actually show that you really only have to check flatness for large n, sufficiently large n, okay? And if A is Artinian, this is the same thing as saying that the finite GP module rho is flat. So the description of what's going on here becomes a lot simpler if you just assume A is Artinian, okay? Also, rho mod m sub A to the n is a finite GP module of p power order. The reason for that is because A is a Noetherian local ring with finite residue field of characteristic p. Okay, and so we can use Renault's results and all these things. Okay, so we have kind of a well-defined thing going on. Let's do an example. Let's let E over QP be an elliptic curve of good reduction, and we'll let rho bar be rho bar EP, which is our kind of our ultimate goal. Okay. O here will be ZP, the p-adic integers, and A will just be O. Then rho, which is rho EP, so this is the full p-adic representation attached to E, represents an element in D flat sub rho bar of A, and the reason for that is theorem 14.3.2 that we spent so much time on in this chapter, and also the fact that rho mod m sub a to the n is nothing but the QP bar points of p to the n torsion on E. Okay, so, like we can actually concretize what we're doing to cases that we actually care about. I mean, to the surprise of nobody, I guess. So what is our goal now? Now that we've got this functor defined in quotes, the goal is to use theory of Fontaine to produce kind of many flat deformations of a given rho bar. Okay, so we will make this more concrete in coming videos. And then when combined with the fact that D flat rho bar is representable in certain cases, which we're going to talk about in a second here, we will be able to actually get a hold of the representing ring, like R flat sub rho bar, I guess you could call it. It then becomes easy to answer all of our questions about flat deformations and do our cohomology computations, etc., at least, again, in the case that the flat deformation functor is representable. That's like the linchpin holding all this together. We can't really move forward until we have representability. So, do we have representability? In fact, before we even talk about that, is D flat rho bar an actual functor? Okay, well, we have to check that. If you consider the simple case where we have a map phi from A to B in C hat O, where A and B are Artinian, we notice the following. We have an obvious map of sets. We can take like du rho bar of this map phi. That'll give us a map from du rho bar of A to du rho bar of B, of course. Okay. Now this takes a representation into GLN of A and applies phi to the matrix entries to yield a representation into GLN B. In other words, it's the obvious map that you think of it is. What do we have to check? We actually have to check that du rho bar of phi, so this map here, maps D flat rho bar of A, which is just sitting inside of here, actually into D flat rho bar of B. We need to check functoriality of this proposed functor here. Now, it turns out this is true, and this is part of the following result, which is Ramakrishna's theorem from his thesis. Okay, so I will state the theorem today, and we will begin to look at the result and its consequences and its proof next video. So theorem 14.4.1, Ramakrishna. The association that sends A to D flat rho bar of A from the category C hat O to the category of sets is a subfunctor of du rho bar. So indeed, we have what we want. In particular, the thing we have to check is what we just said above. Given a morphism phi from A to B in C hat O, du rho bar of phi applied to D flat rho bar of A is indeed inside D flat rho bar of B. Moreover, if rho bar has trivial centralizer, which will happen if rho bar is absolutely irreducible. I think we've actually already talked about this back in the minimal case of R equals T. Then D flat rho bar is representable by an object R flat rho bar, and that object is in C hat O. Okay. By universal properties, this will give us a map from RU rho bar to R flat rho bar, and it turns out that map is surjective. Okay, so this is Ramakrishna's theorem, which we'll begin to look at next video. Have a great weekend. Thanks for watching, and I'll see you in the next one.